Okay. So I guess my first goal is I need to sweat. I don't know how to start you off because I know you watch some videos.
Hmm.
I don't know what would be repeats. Okay, I'm just gonna start you off. When I'm saying something and you've heard it before, just let me know and we can just skip past it.
All right.
The first thing I'm gonna do is I'm gonna send you a link to. So what's your prior experience? You're like completely new to programming?
I did have a couple of experience, but not like too deep in it, you know. Like I just
Okay.
know to make a couple of small stuff.
Okay. What are your goals?
I want to like want to get deeper into programming in general because for a while I always had these ideas for like kind of complex systems that I would really want to make, but I couldn't. I didn't have the ability to because like my skills are pretty, how to say it,
Okay.
pretty limited.
And what are some examples of complex systems?
Usually I had that idea for like an AI system for an enemy, but like
Okay.
I didn't know how to implement at first, so I just gave up on it.
Okay, game AI is a lot of algorithms. It's quite
Mm,
technical. Okay, so it looks like you're more interested in algorithm design. So I think
yeah.
okay, so I tailor what I do in each session to what the person wants. So since you're interested in algorithm design, I'm going to move us towards that direction.
Hmm.
Okay, so I'm going to send you a link on Zoom chat. Could you open that on your end and share your screen with me?
Yeah, just give me a second.
Okay.
Right. Um, you see?
Yes. Could you zoom in a little bit, maybe three times? One more time? Perfect. Okay. Hmm. So, have you seen the add two numbers thing?
Yeah.
Have you seen nummin?
I don't think so. Don't
Okay.
watch far enough. Like,
Have have you done like adding and subtracting a number all in the same line?
yeah.
Okay, okay. So it seems like nummin. Okay. Could you write num dash min?
And you
Num
say again?
like three. Sorry, nummin. So num
NUM.
dash.
Yeah.
That's a hyphen. That's the
Uh,
minus
uh,
symbol. Yeah, min.
like MIN.
Yes, perfect. And now opening parentheses.
Mm-hmm.
Now write two numbers separated by a comma.
25. 5.
Perfect. Okay, that's closing parentheses. Okay, before we run this, what do you think is going to happen?
Um, I don't like. I don't know.
Just guess. Any guess.
From what I can see, like it's gonna subtract like 25 to 5. I'm not sure yet.
Okay, that's subtraction's a good guess. Let's run it. Let's see what happens. Five. Okay, how did we get five?
Hmm. I have no idea. Um,
Okay, I would like you to keep changing the numbers and keep running it and figure out what this is doing.
so tries to find like the least number.
Yes, it gives you the smaller of the two numbers. So min here at my end is short for minimum.
Yeah.
Okay, so unlike plus and minus or multiplication, they're all like symbols, but this is a word, right?
Mm,
We have two numbers. We're performing operations on them, but this operation is not a symbol. It's a word. Now, if you think about it, in mathematics, there are an infinity of mathematical operations. We could do so much with numbers, but we
hmm.
have so few symbols. plus, minus, times, divide. We're going to run out of symbols. And so we have to start using words like this one.
Mm.
Okay? Yeah. Can we add, like, don't delete anything. Just add this whole thing to a number.
Say again?
Don't delete, but add this whole thing to another number.
Oh, like a plus sign? Like
Yes, yeah.
like that.
Yeah, let's try it. You see what's happening?
Mm. Yeah, it recognized the whole thing as like a number, right?
Yeah. And how did we get 33? Can you break that down for me?
It's like 1 plus 32 gave us a 33.
Okay.
So it
So,
found the
yeah.
minimum of number, right?
Yes. So these operations can mix and match, right? First we did the minimum and then we did addition, right?
Mm-hmm.
Could we move the plus 32? Can we move that next to the 1?
The Say
Yeah,
again?
so can we do 1 plus 32?
1 plus
Yeah,
like change the
perfect. 1 plus 32?
2, right? Like that, yeah.
Yeah, no, but one yeah, sure. Can we delete the 32 on the outside? Yeah,
Yeah.
perfect. Okay. Yeah, can we run this? Okay, you see what's happening?
Yeah. It still gave us the minimum number.
Yeah. Notice how the addition's
But
happening
mm,
before the minimum?
um yeah, yeah. The 1 plus 3.
Yeah. So that happens first. So we get 4, and then it checks, okay, which is smaller, 4 or 2? Oh, 2 is smaller. Produces 2. You see that?
Yeah, yeah.
Okay, so there are a few key takeaways here. First, programming is like using a calculator, which is not surprising because a calculator is a computer.
Mm-hmm.
Second thing here is that there's a notion of order of operations. In what order are the operations performed? So here we add first, and then we perform the minimum operation. Okay?
Okay.
All right. Let's try something different. So far we have covered arithmetic, and let's move forward in time a little bit, and let's go to an idea first. Well, history says the history we learn now says it's first introduced in Persia, which is algebra. Let's introduce algebra. Could we delete everything here?
Yeah.
And let's do x equals 1. Sorry, equals.
Sorry.
Yeah, that's all right. And then new line, x. Now, before we run it, what do you think is going to
Mm.
happen?
Um, is it gonna give us 1?
Okay, let's run it. Okay, so it's,
Oh.
why did it give us 1?
Um, we assigned the 1 to the x.
Okay. Can we change the x to x plus 1?
X plus 1.
Yeah, let's run it. Okay, we got 2. What did we get 2?
Because the x is already assigned to 1, so we
Mm,
just
okay.
eh, so we just added the 1 to the x, so it gave us a 2.
Yes, perfect. So this is the idea of variable substitution. Whenever it sees
Mm.
x, it sees 1. Okay.
Yeah.
Can we swap the two lines? Can we put x plus 1 first and then x equals 1?
Okay.
Okay, before
Like
we
that.
run it, what do you think is going to happen?
I think it's gonna come out as 1.
Okay, let's see.
Oh,
X is unbound. What does this mean?
it is used, but not. Wait, let's move that. It is used, but not previously defined. You may need to run the program or check the dashes and capitalize in the names. So I'm guessing the x is unbound to a variable, right?
Mm-hmm.
So it just gave us a null.
Okay. Yeah, so it doesn't know what x is.
Yeah.
Okay, so here we know there's a notion of time. It's like the order of operations, but across multiple lines. Line 2,
Hmm.
x plus 1, it hasn't seen x equals 1. That hasn't happened yet. Okay?
Okay.
So when he sees x, he gets confused, like, oh, I don't know what x is. Hasn't been defined yet. Okay. So let's swap back the two lines. Let's bring it back.
So the two lines, right?
Yeah, yeah, to the correct version. Let's bring x equals 1 back to the top. Okay. Now let's try something different. Could you create an empty line between the two lines?
Yeah.
And let's write x equals 2. Now, before we run this, what do you think is going to happen?
I'm thinking it's gonna like set the x to 2 and then more like add the x to 1. So it's gonna give us a 3.
That's a good guess. Okay, let's run it. Let's see. Oh, what happened?
Wait, hang on. The declaration of a name conflicts with an aerial declaration of the same name. Oh,
Okay, what does this mean?
they both have the same name, but different values.
Okay, yeah. So whenever we define a variable or we assign a value to a variable for the first time, we say that we are making a declaration. We're declaring
Mm.
x to be 1. And different programming languages will have different answers here. In some programming languages, you will get 3, just not in this one.
Mm-hmm.
The idea here is that when you declare a variable, you would only do it once. Can't do it again. It's like the declaration of independence. Once you declare independence, you have declared independence. You can't declare independence again, right?
Yeah.
All right. So here we can't use the same name. Let's change x to that x equals 2 to y equals 2.
All right.
And let's change x
Oops.
plus 1 to x plus y. Let's run it. Very good. So we can have more than one variable. We can add variables together. Can we change
Yeah.
y equals 2 to y equals x?
Should I run it?
Oh, yeah, yeah. Ah, x equals 2. So we get 2 back. Why do we get 2?
Um, is it because like previously like we added an x to 1, so it saw x as a number, not
Hmm.
something else. So when I said y equals x, it saw it as 1, so it gave us y equals 1.
Perfect. Yeah, that's the correct explanation. Yes. Okay. So now we have understood a bit of algebra. We have variable substitutions. Okay, great.
Hmm.
Let's move forward into another idea in algebra, which is functions. Let's delete everything. So to write a function in this language, it's a bit different. First have to write fun
Fun.
space. Next, a function needs a name. Well, let's call our function f. So let's just write f.
If
Let's do
Mhm.
lowercase f. Yeah. Opening parentheses. Next, we need to give this function inputs. So let's call this input x.
Like inside the parentheses, right?
Yes. All right. And after the closing parentheses, let's write colon. Oh, that's a semicolon. Only
Oh,
in
I
a
sorry.
colon. Perfect. Yeah. A new line. Let's do x plus 1. New line. E and D.
Say again?
3 letters. E and D.
Oh, okay.
Perfect. Now notice how it's all highlighted. So we just defined a function. So this is a bit special. Let me ask you, what is a function?
As far as I know, like it's a box of instructions that you could use and like it will give you something back or do something for you.
Yeah. Or put differently, a function is something that takes inputs and gives back outputs. You give it something, it gives you back something. Okay?
Hmm.
So a function has two things, inputs and outputs. And it also has another thing. It has a name. So if we look at this function we just defined, the name is f. F is the name of the function. It needs a name so that we can refer to it later. Next, it
Hmm.
has inputs. In programming, we say parameters. So we say the function f has parameter x. Finally, a function, it needs to produce an output. How does it produce an output? Well, it uses the thing on line 3. We call that the body. The body of the function is what produces the output. So in this case, it adds 1 to the input, and whatever's the answer is the output. Okay?
Hmm.
Now, the line 4n, that denotes the end of the body. That's how we know the function is done. Okay?
Okay.
All right. Let's run this and let's see what happens. Nothing. Nothing happens because we
Yeah.
didn't use the function. We just say it exists. All right, let's create a new line. Let's write f, opening parentheses, and any number you want.
5.
5, perfect. Let's close it and let's run it. Get 6. Okay, so in mathematics, we say we apply a function, but in programming, we say we call a function. Why did we get 6 here?
Uh, I think because like we did like added x to a 1 and like it asks for an x, so we gave it a 5.
Perfect. Okay, so the input, the parameter x takes on the value 5. Great. So notice how there's variable substitution. When it sees x, it sees 5. All right.
Hmm.
So the same idea of variable substitution still applies to functions. So our understanding of algebra in this programming language has now improved. Right. Okay, notice how there are two windows in front of us.
Yeah.
The window on the left, we've been typing in, and that's our program, right?
Yeah.
Window on the right seems to be giving us answers. Let's notice how on the window on the right, we can sort of type stuff into it. Could you call
Yeah.
the function f on a different number on the window on the right here?
Okay. 2 or 3,
Perfect. And now
like
let's hit
that.
enter. Ah,
Oh,
notice how it gives us an answer again.
yeah.
Okay. Let's can we do call f on an addition? So f opening parentheses, add two numbers.
Like 2 plus 3. Oh, 4.
Perfect. Yeah. Very nice. Can we do call f on a number?
Um, like 5
Yeah.
plus f,
Oh yeah, yeah, sure, yeah. While we're on this topic, yeah.
like that.
Yes, perfect. Let's no, don't know. You hit enter, hit enter.
Okay.
Yeah. Wait, can you hit enter? Is it working?
Yeah.
Oh no, you have to hit enter. Because if you hit run, it deletes
Ah.
everything.
Oh,
Yeah.
sorry, sorry.
No, it's
Yeah.
okay, yeah.
Let me do.
Yeah, yeah, yeah. It happens a lot. Okay. Yeah.
Now I hit enter.
Yes. Very good. Now, notice whenever we call the function f with a different number, like we didn't change the function f. We didn't touch our program at all, but we keep getting back new numbers, right?
Mm-hmm.
Yeah. So that's a very cool thing about functions. Functions, it can give you back new things, even though you didn't modify your program, right?
Okay.
Another thing is that this function, notice how we can like add stuff to it. We can pass in the result of an addition, right? It's sort of like what
Mm.
we did with nummin just now, if you remember.
Oh, yeah, yeah.
Well, that's because nummin is a function.
Just like the f, right?
Yes, it was just called differently.
Oh.
Um, in fact, we don't even have to call it f. We can call it anything we want. In mathematics, they like short names because you can write less. But in programming, it's very easy to type stuff in. And we prefer more descriptive names, more helpful names. This function f, what is it doing?
It adds to the number we
Adds.
give it. Yeah.
Let's be more specific. What is it adding?
Um, uh, I kind of forgot the word.
One.
Yeah, one, it adds a one to the
Mm.
x we
Adds
give it.
one,
Yeah.
right? Adds one. Wouldn't that be a better name?
Yeah, I told you.
Yeah. Can we change the name of the function from f to adds one?
Yeah.
Okay. Very good. Can we lowercase the a? So in this language, the function names are lowercase. Yeah.
Okay.
All right. If we run it, what will happen?
Oh,
Hmm.
so should I change it to that? Like adds one.
Yes. Now f loses meaning. Doesn't exist anymore,
Yeah.
right? You have to refer to it by its new name. So how do we fix this?
We change the f to adds one. And we give it
Okay,
like,
let's do it.
yeah.
Okay, let's do it. Nice. See, that's why the name of the function is important. The name, that's how the programming language knows what function you're referring to, right?
Yeah.
Okay. All right. So far we have been covering the mechanics of programming. We have covered arithmetic, performing operations on numbers, and we have covered a bit of algebra. We have variables and we have functions. Okay,
Mm-hmm.
great. So have you seen all of this yet? Or is this like new stuff for you?
Like till yeah, yeah, I think yeah.
It's new?
No, I mean like I think the some of it like are new to me and like the rest are I've known it before, but I didn't know that it's that deep.
Okay. Okay, great. Okay, so I'll do a bit of explaining now.
Mm-hmm.
So the first thing I have to explain is the differences between the two windows. The window on the left, we call it our definitions. This is where we define our program. We can define things like we can define adds one here. The window on the right, we call this the REPL. That's REPL. Stands R for read. It reads what you write. E for evaluate. So in the right window, can you do like one plus one?
Oh, okay.
Yeah. Okay, so it reads what you write. It evaluates it. So evaluates just means simplify. Takes one plus one and simplifies it to two.
Mm-hmm.
Another way of understanding evaluate is it means to turn into a value. So evaluate, that's why that's the word value in evaluate. In programming languages, when we say value, we mean something that cannot be simplified anymore. So two cannot be simplified. Two is two. So that's a value. So
Uh-huh.
it turns your expression, your one plus one, to a value two. So evaluate. P stands for print. Once it has an answer, it prints it out. So we see a two here. We print it out. L for loop. Loop because it lets you do this again and again and again. Okay. So that's
Okay.
REPL, REPL, read, evaluate, print, loop. You don't have to know this. I'm just telling you. Okay.
Yeah.
All right. Let's shift gears a little bit. I want you to delete everything in our program. Oh yeah. Oh wait, sorry. I should also mention the reason. So the not all languages have a REPL. This language has one. So a REPL is very good for getting feedback very quickly. And this language is designed for beginners, and so you can get feedback very quickly. Um, so in your free time, if you want to play around, I recommend that you just open this up, play around with things, try things out. You'll learn a lot. Okay.
All right.
All right. Okay. Sorry. Okay. Let's shift gears again. So I'm gonna introduce some very unique ideas. So you talked about having ideas for complex systems, but you can't seem to execute, right?
Yeah.
So it's not your fault. Like most traditional computer science courses, they they don't train they don't train like the kind of thinking that lets you go from a blank page to a functioning program. They don't teach you that.
Yeah,
So this idea of like, okay, how do I systematically go from nothing to something? That's actually very difficult. And in my sessions, I will teach you some ideas as to how do we do that? How do we systematically go from nothing to something?
that would be great.
Yes. So it's going to begin with this, and it's going to sound crazy, but just humor me, okay? I would like you to write the number
Mm,
5.
right?
I would like you to run it. Ah, 5 is 5, right? Right, 5, we can
Yeah.
write 5. Okay, now let me ask you, what does 5 mean?
Um, it's a number.
It's a number. Okay. Just 5 is a number, right? 5 is 5. Doesn't mean much. What if I say 5 degrees Celsius?
Oh, then it's a temperature.
Temperature. Okay. How about 5 kilograms?
It's a weight.
Weight, right? Notice how they're all 5, but depending on whether I say degrees Celsius or kilograms, it means something a little different. It means more, right?
Yeah.
Okay. There are two worlds. There is the world of information. So these are ideas and facts about our real world, like
Hmm.
5 degrees Celsius. And there's the world of data. Data is what the computer sees. Like this computer, that 5 in front of us, that's data. That's all the computer sees. It does not know its temperature or kilograms. It just sees the number 5.
Yeah.
Okay. So we may see 5 degrees Celsius, and that's information to us, but a computer will only see 5. Okay.
Okay.
So this sounds philosophical, but it's a very practical idea. Because I claim that our role as programmers is to facilitate the interaction between the world of information and the world of data. We turn information into data, perform operations on data, and convert data back into information. We say we encode information as data. Another way you might hear this is we represent information as data. Okay?
Yeah.
So another way to understand everything we have done so far is that we have been encoding information as numbers and operating on numbers with arithmetic and algebra. Okay.
Uh-huh.
Now let me ask you, can we encode all information as numbers?
Um, I'm not sure. Like you mean like just give it a number?
Well, given some information, for example, like um my name, like Marvin, can we encode that as a number?
Ah, I don't think so
Why not?
because Marvin has letters.
Letters. Okay. Do you know the saying that computers are just zeros and ones?
Oh, yeah.
Yeah. Have you heard of Unicode?
Yeah, yeah.
Unicode. So Unicode, what it does is it converts letters to numbers. And then,
Oh,
like for example, when let's say like we're texting, you send me like a text, the words, the letters become numbers. These numbers are sent over fiber optic cables, like waves in the air, and it reaches my phone, and it converts the numbers back into letters through Unicode. Unicode is a convention for converting between letters and numbers,
uh-huh.
right?
Yeah.
So can we encode all information as numbers?
Yeah.
Yeah, right? Yeah, computers are
Yeah.
zeros and ones. So computers can do a lot of things, but fundamentally, computers is just a calculator. It's just operating on zeros and ones.
Oh.
Okay. Next question. Do we want to encode all information as numbers?
Uh, I don't think so. Like,
Why not?
well, thinking about it, I don't think we can only like convert it to numbers since the computer works on zeros and ones, right?
Mhm.
So impossible unless you make like a new different type of computers.
Okay,
I'm kind of
let
going,
me give.
yeah.
Yeah, sorry, go on.
I'm sorry, like I'm kind of going far off it. Like I think I'm saying something wrong. Like isn't like the isn't the answer like something like you? I think you meant something else. That's what.
No, no, no. You understood me
Uh,
perfectly. Your answer is very good.
no, all
Um,
right.
this is all part of the process. Like I ask my questions like this to make you think, and you are thinking very hard right now, so that's good.
Hmm.
But I have a counter example. So not a counter example. I have a counter argument. You said that computers are zeros and ones, so we must convert everything to zeros and ones, right? Everything must be numbers.
Yeah.
Okay. Now let me ask you. You and I, we are talking right now.
Hmm.
I am conveying information to you. You are conveying information to me. We are transmitting information to each other. But are we talking in numbers?
No.
No, we're not talking in numbers, right?
Yeah.
We're talking in words, language, right?
Yeah. Yeah.
Language is a way of encoding information. Doesn't run on a computer, but it's still a way of encoding information. And if we talk in numbers, like, Morse code,
Yeah.
yeah, imagine if I'm talking to you in Morse code, would you understand me?
No.
I mean, yeah, unless you know Morse code, but like, if we talk, let's say you and I, we know Morse code and we talk in Morse code, this
Yeah.
lesson cannot be an hour. It'll be 5 hours at least, right?
Yeah. Yeah.
Because it's very inefficient, very slow, um, and also easy to make mistakes. Like in like the World War, people talked in Morse codes because they have no choice. And you have a room full of people listening to beeps, like beep, 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 like people listening to that all day, and they're writing one
Yeah.
letter at a time. And anyone could make a mistake. So they have a room full of people doing it. So to make sure that like not like they don't make mistakes. But that's super inefficient, right?
Yeah.
It's terrible. So there's this second idea, efficiency. We don't talk in zeros and ones. We don't talk in Morse code. We talk in language. Encoding information, it also needs to be understandable.
Yeah.
So this means that we don't want to encode all information as numbers. Sometimes we want something else, like words, for example. Okay. So now we are going to introduce a new way of encoding information. Let's delete that five.
Yeah.
I'd like you to write double quotes.
Yeah.
Hello, comma space, world. Okay, let's run this. Hello, world. We didn't get back a number. We got back a different animal. We got back a string, like a
Oh.
string of characters. Yeah, we call this string in programming. Have you seen this before?
Yeah. Like I've seen it most of the time.
Okay, you are familiar with this. Good, good. So a string. So this example, hello world, it dates back to like the 1970s. Back then, there weren't many programmers. It's a very new field. And this guy, he wrote a book on how to program, and he used this example, hello world. So it's a very historic example. And ever since that day, every book, video, lecture, all uses this example. It's sort of like a rite of passage. When you're learning programming, you're probably going to write this. So today, you've passed the rite of passage. You have reached a very important milestone of your life.
Right.
Great. Okay. You can do something special later, maybe. You can celebrate. Okay. So we have new ways of encoding information now. We have strings. Just now we had numbers. So this is the first time we are going beyond a calculator. We are now operating with strings. And
Yeah.
just now we had numbers and we can perform operations on numbers. We can perform arithmetic on numbers. Can we now perform arithmetic on strings? Could you add this string to another string?
Um, I don't know.
Let's try it. You can't know unless you try it.
World
Okay,
like that.
perfect. Yeah, that's right. That's right. Hello world, hello world,
Oh,
right? So the same
yeah.
way we can add two numbers, we can add two strings. Hmm. Can we change the plus to a minus? Okay,
I should. Yeah,
let's
run
run
it.
it.
Yeah.
Yeah.
Oh, evaluating this minus expression error. The left side was evaluate like same as triple, right?
So
Hello?
the minus operator expects to be given two numbers.
Yeah.
It doesn't work with strings. It only works with numbers.
Oh.
Hmm. So even though there exists a notion of arithmetic on strings, we can perform operations on strings. These operations are fundamentally different from numbers. Okay.
Hmm.
All right. Um, let's try something different. Can we delete everything?
Yeah.
I'd like you to write double quotes and five. Let's yeah, let's run this. See what happens. Okay, nothing special, right? We wrote hello world, we got back hello world. We wrote five in string, we got five in string.
Yeah.
Okay. On the new line in the program, could you write the number five?
Say again?
On the new line in our
Oh,
program,
yeah.
let's create a new line and run number five. Perfect. And let's run this. Okay, nothing special. Now, bit of philosophy again. Now that we have strings, and strings are a series of characters, and to write a number, you have to write a series of characters. Why do we need numbers? Why not use strings for everything?
Ah, um, I'd say because we want the computer to understand the difference.
For example.
Yeah, for like example, like we have a five as a string. Let's say
Mhm.
hello world five times. You add like the five. So you wanted to see the like five within a string. But for the five as a number, we could make
Okay.
like five minus two, for example.
Hmm. Very good answer. Yes. Yeah. Like these are different forms of data. We say these are different data types. So a number is a data type, a string is a data type. So the computer understands it differently, and so the computers can do different things with them. The
Mm.
operations are fundamentally different. Very good. So while the same piece of information can be represented with multiple data types, there are strengths and weaknesses to each one. For example, we can subtract two numbers, but we can't subtract two strings, right?
Yeah,
Okay, very good. So, to summarize, we've covered numbers and strings, and there's a notion of arithmetic for each one. Great. Okay. Um, okay, now we'll cover a new data type. So these data types, right, they encode important information, like numbers they encode numbers, right? Like, so we get the whole field of mathematics in our computers. Very powerful.
yeah,
Strings, like humans, we communicate with language. Language is a very important idea to civilization, developed since the dawn of humanity. Words are important, so we have strings. So that's a third idea that's also very important that we want our computers to understand. That idea is decisions. We want to encode decisions in our computers. It can be
yeah,
said that life is a series of decisions. Our computers operate on decisions. Our computers are making decisions all the time. So a decision is important. A decision is fundamentally yes or no. For example, your decision to come to my office hours? You must have said yes, right?
Yeah.
Decisions, very powerful. So, you hear yes, no, on or off, left or right, true or false, right? These ideas of dualities. In programming, we call them Booleans, named after George Boole. He's a
Mm.
mathematician who studied these things as mathematical objects. In programming, these Booleans, there are two Booleans. There's true and false. So true and false. Let's delete everything in our program
All right.
and let's write true. That's TRUE. Let's run it. Okay, notice the true is red in color. We get back
Yeah.
true. So true is a value in this programming language. Can we replace the true with false? Let's run it. False, right? Another
Yeah.
special value. So these two, true and false, are booleans. So numbers, you have 1, 2, 3, 4, 5, 6, 7, 8. You have a lot of numbers. Strings, you have hello, world, goodbye, like a lot of words, a lot of strings. You can have many strings. But
Yeah.
booleans, there are only two, true and false. Nothing more. Okay? All right, so booleans. Let's write false and true. That's false, A and D, true. Okay, let's run it. False and true is false. All right,
Oh.
so yeah, notice how we have two booleans and we reduced it to one. It's the same way we can add numbers and strings, we can also add booleans. So there's a notion of arithmetic for booleans. Okay, can we change the and to an or? That's OR.
Oh yeah.
Okay, now let's run it. False or true is true. Okay.
Oh.
So the bolded thing in the middle and now the or, we call these Boolean operators. They operate on Booleans. Okay. All right. So now I'm gonna share my screen for a moment. Give me 1 second as I set this up.
Yeah. Take your time.
And I think you might have to stop sharing your screen in order to see my screen. We'll see. I've
All
heard
right.
mixed reports about this. Okay. Share. So let me know once you see my screen.
Oh yeah.
Okay, so I know this looks scary, but it's not. It's actually very easy. We call these truth tables. Just now, we saw false or true is true, false and true is false. Why is that? So the short answer is that these tables here are the definitions for arithmetic for Booleans. Um, Here we use zeros and ones. Zero is false, one is true. Um,
Yeah.
Remember how we said that computers are zeros and ones?
Yeah.
These are the zeros and ones. These are it. These are the zeros and ones. Um,
Oh.
So each one of this is a truth table. They tell us how the zeros and ones become an answer. So for n, for example, 0 and 1 is 0. False and true is false. This is the OR table. 0 or 1 is 1. So false or true is true. Okay? Conceptually, these are like functions. They take in input, they produce output. You can even see input and output here.
Yeah.
Now, the diagrams above here, these are logic gates. These are physical embodiments of the function. These are physical devices, like you can hold them in your hand. These, there are thousands, millions, billions, trillions of these things. These are very tiny. These tiny things, we have many of them. They make up our computers. These things make
Oh.
up our computers. This is what allows computers to exist. So these lines here, these are wires. They hold electricity in them. If
Hmm.
electricity is flowing in a wire, it's true. If it's not, it's false. So if one wire is so with when a wire there's electricity flowing in it, I'm just going to say it's hot. When a wire is hot, it's one. When a wire is cold, it's false. So if one of these wires is hot, then there's no electricity flowing out of the wire on the right. Whereas for OR, if there's one wire that's hot, one wire is cold, we have electricity flowing out of this from this wire. Okay?
Oh,
Yeah. So our computers, they're a soup of zeros and ones, and these logic gates are stirring the soup, changing the zeros and ones. And this happens very quickly. Like there are at least that depending like how fast your computer is, there are like millions of these happening in the 1 second. 0 1 1 1 0 0, they're constantly changing. And this is what allows computation to be possible. Okay.
okay.
So as programmers, we don't need to know all this. Uh, for operators, we only need to know three: not, and or. The not operator, it just flips the boolean. If it's false, becomes true. If it's true, becomes false. For and, it's very simple. When one of the booleans is a zero, it's false. So if you see one false here, then the result is false. For
Okay.
or, if you see one true, then the whole thing is true. So why is it like this? The short answer, that's just the way it is. The more nuanced answer is that, let's say I ask you, do you have an apple and a banana? And you only have a banana, you say no. I don't have an apple and a banana. I only have a banana, so it's false.
Yeah.
But if I ask you, do you have an apple or a banana? You say, yes, I have a banana. Yes, the answer is yes, it's true. Okay?
Okay.
So if there's one false here, it's all false. That's for the AND table. For or, if there's one true, then it's all true. So these three, not, and or, these three are basically the only ones you need to know as programmers. Well, you told me you were into algorithm design. If you want to perform efficient algorithms, sometimes you have to
Yeah.
resort to other Boolean operators. Because like when you're trying to write something that's very, very, very efficient, you have to talk to the computer directly. The computer talks in zeros and ones. So
Oh.
you have to speak its language. Sometimes you have to use XOR. Oh, yeah, XOR is a very important one. Sometimes you have to use this.
Ah,
What is
yeah.
XOR? Okay. Since you told me you're interested in algorithms, I'll tell you what these other operators are. So XOR is exclusive OR. X for exclusive. It's the same as OR with one major difference. If it's both true, then it's false. Okay?
Okay.
Like,
So, yeah.
yeah.
Yeah. Just like the or, but if it was both one, it's false, right?
Yes. So like for example, like your parents ask you, do you want like let's say you're a kid and your parents ask you, do you want ice cream or waffles? You say, I want both. Your parents will say no. You can only choose one.
Oh,
Right?
okay.
So that's exclusive or. That's what exclusive means actually. Exclusive is you can't have both at the same time. Like in a relationship, if you say you're exclusive, right, you can only date one person, you can't date more than one, right?
Ah, yeah.
Yeah. Okay. Nan, when you see N, it means not. So if you notice
Okay.
Nan is opposite of N. Like zero zero
Yeah.
1, this is 1 1 0. Nor, same thing. 0 1 1 1, opposite is 1 0 0 0. Okay?
Okay.
So yeah, so the N is not. Uh, X nor is exclusive or, but with not. So if you notice 0 1 1 0, 1 0 0 1.
Yeah,
Okay?
like the opposite.
Exactly. So this is the arithmetic for Booleans. These are the operations. You should at least know not and or, but it's good to know the rest if you're trying to write an efficient algorithm. Okay, so that's it. And I'm going to introduce one more thing.
Yeah, go ahead.
Okay, can you share your screen again? Stop sharing mine. Okay, I'm going to write something in Zoom chat. I'd like you to copy and paste it into your thing, your program. Okay, I just pasted it. Can you copy that and paste it in and don't run it yet?
Yeah, just give me a second.
Take your time. Okay, now before we run it, what do you think is going to happen?
Well, I see a circle, a 30
Okay,
and a solid in the red.
okay.
I'm guessing that's the size of the circle.
Mm-hmm.
The solid, I'm not sure. Like,
Okay.
and the red is the color.
Okay, let's run it. Let's see what happens. Ah, draws a circle.
Oh,
A solid circle, red in color.
oh.
Hmm.
Okay, like the solid like means filled, not
Yes.
like just a circle. Okay, okay.
Yeah. So this language has another data type, and that data type is images. A data type doesn't need an existential reason to exist. Doesn't have to be fundamentally philosophical. A data type could just be useful. This language is designed for beginners, and sometimes beginners are children, and images are fun to work with. And so this language has data types. Sorry, has images as data types. Okay?
Yeah.
All right. So we'll explore this more in the future. For now, okay, we're gonna start wrapping up with 3 more minutes. So to summarize, we have covered 4 data types today, and we saw that we can perform arithmetic on each data type. Arithmetic means something a little bit different for each data type.
Yeah.
So these three number strings and booleans, they're like cash. If you're lost in a city, but you have cash, you can probably get what you need. If you have information you want to encode, you'll probably need one or more of number strings or booleans.
Yeah.
Okay. I'd like to end my session by asking the students, what is one thing you learned today that stuck with you?
Um, Probably like the truth tables, like XOR, NAND, and NOR.
Cool, cool. Okay. We have 2 minutes. Do you have any questions?
I don't think so.
Okay. All right. And how's this pace? Is this too fast or too slow?
I think it's perfect.
It's perfect. Okay.
Yeah.
Okay. Uh, all right. Yeah. In that case, oh, that's it. Well, I thank you for coming to my office hours, and I'm very happy to be able to help you in your journey. And I hope to see you again.
All right. See you later.
Okay. Oh, wait. Essentially, sorry. I got one question.
Mm.
Do you want homework?
Oh yeah, of course, yeah.
Okay. I'll email you homework. And no pre if you
Yeah.
don't have time, it's okay. No pressure. But if you have time, doing homework is good for your health.
Yeah.
Okay. All right. Bye bye.
All right, thank you.